this session will be about coding theory. And our first speaker will be Ron Kuan from Tel Aviv University. We'll talk about the joint work with Tamo about a new improved way to repair Reed-Solomon codes using non-linearity. Thank you.
Hi everyone, thank you for the introduction, Noga. So I'll be talking about nonlinear repair of Reed-Solomon codes, and this is a joint work with Tamo. So throughout all this talk, we are going to discuss only linear codes, that is linear subspace of dimension k. We're going to use the common notation, which you all know. The finite field is going to be right of order q. And we're going to discuss only MDS codes, which have the MDS property that the code can correct from any n-k erasures. Good, so our work falls into a greater topic called coding for distributed storage systems. And you can imagine the following scenario. Well, you have a file and you want to store it into the cloud, into this big storage system, and you cut it into k chunks of data. Each such chunk is going to be a symbol in a finite field of order q, and these k symbols together are going to be encoded using the MDS code to an MDS code word. Well, we see here the code word C1 up to Cn. These are the symbols of the code word, and then each symbol is going to be distributed to a different server. Okay, so the pictures looked like that. We have n servers, and each node stores a symbol from the code word. Now, a common problem in storage is that a node fails. And when a node fails, we bring up a new replacement node, and each job is to recover the data that was on the server that failed. Okay, so how does he do that? He does that using a repair scheme. And basically, he receives information from the remaining nodes, okay, some function of the data that they store. Well, we see here mu1 of C1, mu2 of C2, and so on. And upon receiving this data, the replacement node basically recovers the data that was on that server that failed. Okay, now the scheme is going to be linear if these functions mu1 up to mu(n minus 1 a linear function, and by linear I mean linear over the base field. So recall that we are working in a finite field of order q, and it has a base field. Good. So the main parameter of interest is going to be the bandwidth, which is basically the total number of bits transmitted from the remaining nodes to the replacement node in the process of the repair. Okay, basically it's the following sum, right? And this parameter is, we want to minimize it, and we want to minimize it because in a real life scenario, when a server falls, and it is not a rare incident that the server falls, it triggers a lot of communication in order to repair it, in order to recover the lost data. And minimizing will eventually, over long periods of time, will make the system more reliable, minimizing the bandwidth. Good, so the first repair that I want to show you is the trivial repair, which is just using the fact that we use an MDS code. Basically, any case servers, any set of case servers can transmit their symbol to the replacement node. Now, upon receiving case symbols, since we have an MDS code, the server can decode the entire code word. It has the entire code word, and in particular, it has that symbol, okay, that was lost. The scheme is linear, trivially. The bandwidth is k times log q, okay? And the question is, can we do better in terms of bandwidth? And this whole area of research started in the paper of Dimakis et al. In 2010, and they proved a lower bound, which is called the Katzet bound, on the amount of bits that is needed in order to repair a failed node. Okay, so D here in the quantity is going to be the number of nodes that participate in the repair. And if we go back to the trivial repair, the number of nodes that participated was K. So if we sign here, instead of D, we sign K, we are back in the regime where the bandwidth was K times log Q. But we see that as d increases, k plus 1, k plus 2, this quantity becomes much smaller. Okay, and another small definition. So code that a repair scheme with a code that achieves this bound with equality for any set of D helper nodes is called an MSR code, And there are MSR codes out there, but we were interested in the code which is called in many ways the greatest of them all, and that is the Reed-Solomon code. Okay, so I'll just, I think that we all know what Reed-Solomon codes are. I'll just say here, the definition is written here, but we were interested in Reed-Solomon codes because Reed-Solomon codes are already deployed in current storage systems. For example, Facebook uses Reed-Solomon code where n equals 14 and k equals 10. So designing repair schemes with better bandwidth for Reed-Solomon codes can find immediate application in these storage systems. So of course, we weren't the first to look on Reed-Solomon codes. It started in the paper by Chen et al., which showed that there are repair schemes that are better than the trivial repair scheme for Reed-Solomon codes. Then Guruswamy and Wootters gave basically complete characterization of linear repair scheme of Reed-Solomon codes. Then, based on their work, Tamo and Bark showed that RS codes are NKD MSR codes for any KD and N. Well, problem solved, right? But the thing is that their construction of Tamo and Bark requires a field size of 2 to the 2 to the n. And they almost achieved an almost matching lower bound, which says that the field size has to be 2 to the 2 to the k. And this is clearly infeasible in practice, right? We don't work with such large fields. So the main goal is to reduce the alphabet size. Okay, and we started looking at this, and the first thing that came up to our mind was, okay, so MSR codes and linear repair by Al-Rabia and Guruswamy in 2019 must have large alphabet size. Okay, so maybe turn to nonlinear repair scheme, and this was also raised as an open question in Guruswamy and Wootters' paper. What is the power of nonlinearity? And our starting point, which became this work, was to look at Reed-Solomon codes over prime fields. And why we did that? Basically because there are no linear functions from prime fields to a proper subset of the prime field, which is linear, right? So as a conclusion, any repair scheme that outperforms the trivial one must be nonlinear when we talk about Reed-Solomon codes over prime fields. And this is exactly what we did in our work. We basically constructed nonlinear repair scheme. As far as we know, it is the first nonlinear repair scheme. And I'm going to describe two theorems. So the first one is that almost all two-dimensional Reed-Solomon codes over prime fields are asymptotically MSR code, and I'll say in a second what means asymptotically here. Another theorem is that a construction of Reed-Solomon codes, not for every regime of parameters, but only for k and d up to n over 2. We show the construction where any node can be repaired using bandwidth that asymptotically achieves the cut-set bound. And we know that this construction is not an MSR code. And by asymptotically in both theorems, I mean that we achieve almost the cut-set bound, but another additive factor of bits, which depends on n. And we say asymptotically because in storage, we think of P, the alphabet size, being larger than n, the number of nodes. Good. So we provided also a lower bound. And I'm going to just skip to the open questions since I don't have much time. But there also is a lower bound which a bit improves the cut-set bound in this specific regime. Good. So open question is basically showing that there are RS codes over prime fields that are asymptotically MSR codes for any NK and D, also providing explicit constructions. We want to show like Tamo and bug, okay, for any NK and D, provide an explicit construction of RS codes over prime fields. And the final open question is to better understand the tension between the field size and the dimension of the code or the length of the code. Okay, we believe that our work was just scratching the surface of this entire field of nonlinearity. And we believe that we can take our techniques and employ them also in other codes, which are not only Reed-Solomon codes, and designing more nonlinear repair schemes. So thank you.
Okay, thank you. And thank you for being on time in this tight schedule. Sorry for writing for everyone. I was trying to locate some speaker. Okay, are there any questions? Yeah, Noah? Just open your mic and talk. Yeah.
Okay, I was just wondering about the upper limit of 2, where that came from, and if you could say a word about your techniques.
Again, what was the question? I didn't hear.
So what was the reason you could do only dimension 2, k equals 2?
Well, it was the easiest case, which is not trivial. And the word about the techniques, we basically were looking at okay, so you when you have an extension field and a subfield, okay, so you take a subfield and you make a subfield plus a subfield, you are again in the subfield, okay, and this thing is highly used in all of the schemes of Wootters and Tamo and bug, and we want to find subset of prime fields that have similarity to this structure. Okay, they are not expanding in sums. So we took two arithmetic progressions. Okay, so if you take an arithmetic progression and you make arithmetic progression plus an arithmetic progression, you don't expand very much. So this is the main idea. I recommend you all to watch the full video, which I discuss in more details our techniques.
Okay, thank you. Okay, I guess we can take more questions offline. Sorry, we are in a tight schedule. Thank you. Okay, so now for our next speaker, Noah. Okay, so maybe you want to upload or share your slideshow.
Yeah, I can't start until the other participant.
Okay, Roni, can you unshare? Thank you.
Thank you.
Can you share now?
Can you see?
Yeah, I can see. Okay, thank you.
Great.
Okay, so our next speaker will be Shutty from Stanford University. And he will tell us about a new way to repair new things, not just symbols or code words, but linear functions over code words. Thank you.
Okay, thank you. Yes, so I've titled this Computing Efficiently on Encoded Data, and this is joint work with Mary Wootters, who's right there. And I'm just going to jump right in. So yeah, similar to before, we have bits, I'm going to say B bits that we want to store, and we have some nodes that we can store these bits on. And the most naive approach would be, without any coding, we're going to just split up the bits into chunks and put a chunk on each node. And then when we want to recover all the bits, we have a total bandwidth cost of B bits to recover a bit stream. And we're interested in this talk in computing functions of those bits. and we want to save on bandwidth cost whenever possible. So the real problem with this naive approach is that if something bad happens to one of your nodes, you've just lost that chunk and you can't recover those bits, and you can't compute functions that depend on those bits. So we don't use this approach, and we know the solution to this using error correcting codes. So in this case, you encode your bits in some code. They take up more space. Maybe they are occupying more nodes, but you can still, for a reasonable code like the MDS codes, you can recover your original bit string with just B bits of download bandwidth. You can compute arbitrary functions once you download the bits. Okay, including repairing a node, for example. And if something bad happens to one of your nodes, this is still the case as long as not too many of your nodes are lost. We focused on the case of Reed-Solomon codes. So as Ron mentioned in the previous talk, these are very important. They're used in systems like Ceph and HDFS. And okay, so in these codes, there are K symbols of a finite field with Q elements. So each symbol is represented by log2 of Q bits, not necessarily 2, just log2 of Q bits. So B is K log2 of Q. And we encode in this code. And we were interested in computing functions that look like this. So some sum over I of lambda I times Fi, where the Fi are the symbols of our finite field that comprise our message, and the lambda I are some arbitrary coefficients from that same finite field. So these are linear functions. And we found that if you had encoded in a Reed-Solomon code, you can compute these functions by downloading just little o of B bits, regardless of what linear function you had chosen. The bits that you download may depend on the lambda I, but it doesn't matter what they are. You will be able to find a way of doing this, little o of B bits. And I found this really surprising because naively at the start of this project, I just assumed that an error correcting code is like a big and bulky suit of armor that will provide protection to your data, but it's kind of slow and bulky, and it'll be difficult to compute on your data because you have to worry about the fact that it's encoded. But our work shows that, at least for the purpose of these linear computations, the Reed-Solomon code is more like the Iron Man armor, because it not only provides protection, it gives some new capability. Specifically, you can compute with just B over log B bits of download bandwidth, that's a little o of B. You can compute any linear function you want of your message. So this is only possible because when you encode in the Reed-Solomon code, you're doing some non-trivial computations and storing the outputs on all of the nodes. So you're able to take advantage of that. When you want to compute this new function, you're able to take advantage of this pre-computed library of functions. Okay, there are a lot of similar problems in the literature. So as just explained in the previous talk, regenerating codes in which you want to repair some nodes that have failed and recover their contents by efficiently querying the other nodes, and coded computation and homomorphic secret sharing and gradient coding. All of these things, there's a lot of work in all of these directions. And in general, you have some notion of encoded data, and you want to perform some computation on it, and there's some measure of bandwidth that you want to minimize. So this is a common idea, and we wanted to study this in more generality than regenerating codes. So we generalized regenerating codes, which are just a special class of linear functions for a linear code when you want to compute the specific code word symbol that was lost. And we generalize that now to all linear functions, which we just thought was a really natural class to consider. So this is like our new problem. And this is our theorem, or this is a special case of our theorem. So if you just imagine, let's fix a rate R and then some sufficiently large prime power Q, then we'll consider the family of Reed-Solomon codes that are full length over FQ to the T. So we work over this extension field, and we use every point in that extension field as our evaluation points for the Reed-Solomon code. Then for any set of coefficients, lambda 1 through lambda k, we can recover this linear function lambda transpose f, where the f1 through fk were our message symbols. We can do that just by making queries to the nodes that hold these symbols of the code word that results from encoding f. And the total download bandwidth is just proportional to n bits. If we think of Q as a constant, this is like B over log B bits at most, if the message has size B bits. So this is an improvement of a factor of log B over this naive scheme of downloading all B bits that you would need to recover the message. And our theorem is more general than this. You can handle some non-participating nodes or failed nodes that don't send any data. And equivalently, you can imagine they never existed in the first place, meaning you can have fewer than Q to the T evaluation points. I'll just note that our results are the best when you use the entire extension field FQ to the T and all of the nodes participate. But you can handle some of them being gone. And you can vary these quantities like Q and the rate and the number of participating nodes. Of course, you can't handle more than 1 minus R times n failures, or else you'd have catastrophic data loss. So that's our theorem, and you can see our paper for the details. One of the perhaps limitations is that, yes, we must have some extension field like FQ to the T, and we can't like directly work over a prime field. So we know there's one way to get around this. If you wanted to perform batched computations on T messages that are each a vector over FP for some prime P, then you could view those messages stacked as like one vector over P to the T. And then you can encode in some code over this extension field, and you can recover the same linear combination of all of your messages at the same time. And when you amortize, our scheme will save you bandwidth, but you can see the extension field has just crept back in. So you really do need some notion of this extension field. And why is that? Well, that you can encode a field element of an extension field like alpha as some vector with T elements in the base field F little q. So here I'm just writing it as U1 through UT. And you can make this play nice with addition. So alpha plus beta in the big field, you get by just adding the corresponding vectors in this base field over the base field. And this is just because the extension field is a vector space over the base field. So we just fix a basis and then we get this mapping. So using this mapping, we can describe what a linear scheme is, and this was also mentioned in the previous talk. So let's say we are a user, we want to recover this linear function sum over I lambda I fi. And what is node I going to send us, right? They have f of alpha I, so that's the evaluation of the polynomial with coefficients f1 through fk, and they have that evaluated at alpha I. Well, this is just some element of this finite field, which is an extension field fq to the t. So like we just saw on the previous slide, you can view this as this t-dimensional vector with elements in f little q. And what this node will send us is just some matrix times this vector. And that'll be an s-dimensional vector instead of a t-dimensional vector. So we get that back and we do something with it. And so A, this matrix A that we multiply with is s by t. And if we can keep s smaller than t, then we've saved on bandwidth versus just downloading the entire symbol. And that's the idea of like a linear scheme. But in order for it to be linear, you also need to do something linear with all of the things you receive. So once you get this s-dimensional vector that's AU, you multiply it by some t by s matrix R, and you have a different R and a different A for each node, that's RJ, AJ, and then you just add everything up. So you'll say the output of the function is just sum over J of RJ times AJ, UJ. Okay, so I haven't told you at all how you find the RJ and the AJ, and I won't have time to do that, but if you found such things, that would be a linear scheme. And when you add all of these up, you have s bits, order s bits for constant q from each node, and the total bandwidth will be little of b. If you can keep the rate constant and q constant and manage to keep s constant, which we do. So the way that we did this at a high level, we found some characterization for any linear code.
Oh, we will need to finish in 1 minute.
Sure, thanks. So the characterization tells you which things you can recover, which lambdas, in terms of the row spans of the AJs. And then we can kind of work backwards from Reed-Solomon codes to find the RJs and AJs. And we end up with B over log B bits. And this turns out to be optimal if you assume a linear repair scheme. So we showed a lower bound, but there is a gap for the dependence on the rate and the fraction gamma of failed nodes. So for future work, we suggest finding the correct dependence on those quantities, generalizing to other parameter regimes like very few evaluation points, beyond linear functions, maybe low degree polynomials, and perhaps using nonlinear schemes like in the pioneering work of Kuan and Tamo that was just presented before this talk. And again, for other codes as well, perhaps. So thanks for watching, and if there's time for any questions, thanks.
Thank you very much. Thank you for being on time. Can you switch to the open problem? Thank you. I didn't have time to read. Okay, thank you. Okay, any questions? If you have questions, you could just open your mic and ask. What do you think about other functions like low degree polynomials, or should it be possible using Reed-Solomon? Or?
See, using our technique, you can compute some polynomials. For example, like each node could square its contents, and then if your k was less than n over 2, then you can view that as a code word in a different code that represents some other message, which is some polynomial function of your original message. So there's some weird functions you can compute, but to get a specific
logical polynomial. Do you have in mind some other code that can do logical polynomials?
No, I just need to read. First, I would read the work of Kuan and Tamo. Maybe there's nonlinear code or nonlinear repair schemes. Maybe will be better suited.
Maybe maybe you can do nonlinear and linear functions.
Yeah,
it's interesting. Okay, thank you very much. So who is next? So I guess it's the expanded paper, right? Sue, you are next.
Yes. Okay.
Thank you. So maybe you can share your slides.
Sure. Okay.
Yeah. See them, right?
Is it good right now?
Okay, thank you. So our next speaker will be Chen from University of Science and Technology at China. And he will talk about I think a very surprising result that improves the well-known parameters of expanded quads. Thank you.
Thank you for the introduction. So hello everybody. Today I will talk about improved decoding of expanded code. This is based on joint work with Kuan from Peking University, Shutty from Johns Hopkins, and Minghui Ouyang from Peking University. Okay. So let me review some basic notations in coding theory that will be used in this talk. So we will only consider binary code in this talk of nonce n, say the code words C1, C2, and so on in this binary code C. And we define distance to be the minimum Hamming distance among all pairs of code words in C. And we define log, the size of C divided by the nonce n to be its rate. So one thing we will use in this talk is that if the distance is delta, then we know the unique decoding radius of the code C is half of delta. So this fact will be extensively used in this talk. Okay. So we will discuss expanded codes, but before, so let's first define expanders. So an expander has two parameters. The first parameter alpha n denotes the size of the subset that we are interested in. The second parameter 1 minus epsilon times d denotes the expansion we are requiring for the in the bipartite graph. So specifically a bipartite graph with n vertices on the left and m vertices on the right, which is d regular on the left, is an expander if for any subset S of size alpha n on the left-hand side is neighbor side gamma S in this talk is of size at least the size of S itself times the expansion parameter 1 minus epsilon times d. Okay. Okay, so this is the definition of expander. So a few remarks. The first thing is that so there is a trivial upper bound on the size of the neighbor set. That's d times the size of S. So expander requires a highly non-trivial lower bound on the size of the neighbor set for any subset that's less than alpha n. So a few more remarks is about the parameters. Usually we think m is less than n, say m is half of n, and alpha is some constant. And the second, for many interesting applications, epsilon is the most half. In this talk, we sometimes some results require epsilon to be less than 1/4, and we also want d to be a constant. And so there are explicit constructions achieving these parameters. So that's all I want to say about expanders. So next, let me define expanded codes, which are well known for the ultra efficient decoding algorithms. So basically, you can think of the expander as the bipartite graph for the parity checks. Okay. So specifically, given expander, we will assign one Boolean variable to each vertex on the left, and then view each vertex on the right as a parity check on its neighbors. So then the expanded code will just contain all binary strings, satisfy all M parity checks. Okay, so there are n vertices on the left, so the length of the code words is n, and the M parity checks on the right. So yeah. So one thing I want to say here is that the rate of the expanded code will be n minus m divided by n. So as long as m is say half of n or less than it, so the rate is a constant. So another thing is that this is closely related to LDPC codes. While LDPC codes requires the right hand to be regular, most LDPC codes are expanded codes. Okay. So let me review some previous work. So expanded codes are, as mentioned earlier, are famous for the ultra-efficient decoding algorithm. Similar work by Stips and Spielman showed a linear time decoding algorithm called belief propagation. So basically, this algorithm can decode 1 minus 2 epsilon times alpha n errors for any expander with parameters. So the size of the subset is alpha n. The expansion is 1 minus epsilon t, 1 minus epsilon d, right? So I want to say this provides a asymptotic good code with linear time decoding algorithm. So in fact, or at least to the best of my knowledge, all asymptotic good codes with linear time decoding algorithm are based on variants of expanded codes. So a few more remarks is that it is foreclosed the distance is at least 2 times 1 minus epsilon times alpha n. So you can see a gap between the decoding radius of the algorithm by Simpson and Spielman and this distance that's like epsilon times alpha n. So there are two works trying to bridge the gap with decoding with a slightly better decoding radius like 1 minus 3 epsilon over 1 minus 2 epsilon times alpha n. So while a natural question is to improve the decoding radius, so before answering that, so maybe we should try to figure out what is the best distance bound one can get from an arbitrary expander. Okay. So our first result shows that in fact the distance of any alpha n 1 minus epsilon d expander code has distance alpha n divided by 2 epsilon minus some constant for any epsilon. Okay. So just compared to the previous folklore bound, like 2 times 1 minus epsilon times alpha n. So we have alpha n over 2 epsilon, so which is better for any epsilon less than half. And moreover, we show this is tight if we only use the property of expander. So there are codes with distance alpha n over 2 epsilon plus little over. Okay. So that's all I want to say about the first result. We give a better distance. The next question will be that given the new bound, can we design ultra-efficient algorithms that decode more algorithms? Specifically, can we decode like in the order of alpha n over epsilon errors? So we also show this is possible. We give a new linear time algorithm that decodes like 3 alpha over 16 epsilon times n errors for any expanded codes, but we require epsilon to be less than 1/4 for this theorem. So I want to say like this improves all previous bounds, like 1 minus 2 epsilon alpha n and 1 minus 3 epsilon over 1 minus 2 epsilon alpha n for any epsilon less than 1/4. But this falls slightly short of the decoding half of the distance. That would be alpha over 4 epsilon times n. Okay, so that's our main result. So let me mention one key ingredient in this in this work that will be this like size and expansion trade-off. So this says that given any expander, say the original parameter is alpha n 1 minus epsilon d, so it's actually a expander for a larger subsets, but with worse expansion parameters. So namely, so you can pick any k greater than 1 and look at the subset of size k times alpha n. The expansion will become 1 minus k epsilon times d. Okay, so you can pick any k for this to get a worse expansion for larger subsets. So that's the key ingredient in this work. So maybe I do not have enough time, so let me just quickly sketch the proof. So the proof.
We have like 2 minutes, okay?
Sure. Yeah, that sounds good. Yeah. So the proof sketch for the new distance bound is just the basic idea is to plug the unique neighbors argument with the size expansion trade-off. Okay, so I will skip this part because it's relatively standard. So let me tell you a little bit more about the size expansion, how we prove the size expansion trade-off. So the basic idea is a probabilistic argument about collisions. So let me remind you what we need to do here. We know the graph satisfies some expansion for subset of size alpha n, and we want to prove like a slightly worse expansion for subset of for larger subsets of size k times alpha n. So basically, so we know like S here has expansion 1 minus epsilon times d times the size of S. We want to prove the lower bound on gamma t. Okay. So the basic idea is like if T has too many collisions, I will pick a random S in T of size alpha n, and then I will try to argue S will also have some collisions, which means that the expansion of S is not great. So this gives me a contradiction that the T should not have too many collisions. So that's the basic idea in this proof. And then let me say a few words about the ideas behind the decoding radius. So the key observation is that in fact we can improve belief propagation by guessing the expansion of the error set. So in particular, so if you remember belief propagation, so we will flip all bits with 1 minus 2 epsilon d wrong checks. So I will replace this by a new threshold, which depends on the expansion of the errors in the string. So yeah, so that's all I want to say about our algorithms. And so just a summary. So
we need to finish in 1 minute. Okay.
Yeah. So the distance is like as I said, like the distance is like at least like alpha m over 2 epsilon, which is tight. So this is a better distance compared to the previous 4-lower bound. So we give ultra efficient decoding algorithms with radius like 3 alpha n over 16 epsilon. The new ingredient is the size and expansion trade-off. So just like summary, so we have so maybe like one interesting question is decoding algorithm for epsilon greater than 1/4. Another regime will be these decoding algorithms, including LDPC codes, and finally maybe can we get some hardness result for decoding the LDPC or expanded codes? So I want to say thank you. Yeah, thank you.
Thank you. Thank you for being on time. Any questions? Do you remember correctly that you no one? Okay, please ask. Yeah.
Oh, okay. Sorry. Have you thought at all about like using this to improve quantum decoders?
That's a really good question. To be honest, like we are learning quantum code at this moment. We haven't. Yeah.
Thank you. I also remember that you have some results about listed coding. Do I remember correctly?
Yes, we do have some. Yeah, we do have. So it's in the bottom slide. So we show like for certain regimes, this decoding radius could be larger than standard Johnson bound. So basically, the reason is like we know this distance is tight if we just use the expanded property. So we will look at just Johnson bound for this distance. So we think that's the standard, and we show we can do something.
But it's like combinatorial. You don't have algorithmic results, right?
No algorithm, but just the combinatorial.
So that's a good question. Okay, thank you. Okay, so who is next? Leonardo, right?
Hopefully everyone can hear me and can see my screen.
I can hear you and I can see your screen. Thank you. Okay, so next speaker is Leonardo Coregliano from Institute for Advanced Study at Princeton, right?
Yes.
Yes. Okay, I think there are a couple of them. Okay, cool. And it will tell us about linear programming for linear codes.
Yes.
Thank you.
Okay, so as we have seen in the previous talk, so we're focusing on coding theory, right? So, and the main problem here is that we are trying to send some code through a channel that potentially has a noise, and we want to resist corruption, right? And the two main quantities that we are interested in are the rate, which is essentially information per bit, and the distance, because the distance measures robustness of our code. As we saw in the previous talk, if you have distance, a number of errors that's less than distance over 2, that's called the unique decoding radius, because you can just decode by looking at the nearest valid code word, right? And we are mainly interested here in actually theoretically correcting this. So in our talk, we're not going to care about algorithmically decoding this. So we're interested in this very basic question, which is how large can the rate be while the distance is still large? And in formulas, these are the two quantities that we're interested in. So it's A2 and D, so it's the size of the best possible code of distance at least D. And R2 delta is the best possible asymptotic rate when the relative distance is delta. So we are particularly concerned in this regime where the distance is delta times n for some fixed constant delta. Now, as you might know, also I will say we are particularly interested in linear codes. As we saw, these are just linear subspaces. And I will remind you that distance for these guys is more easily computed as the minimum Hamming weight of a non-zero code word. Now, as you might remember, the classical results of the literature are first the GV bound. So random codes and random linear codes are quite good. So you can get a asymptotic rate that is 1 minus the binary entropy of the relative distance. Gilbert gave with the random code, and then we have Varshimov with the random linear code. And on the other side, we have Michaelis, Rodemish, Ron-Zewi, and Welch gave the famous LP bound that gives you an upper bound that says, okay, larger than this rate, you cannot have any code. So this is a small graph that shows these two curves. So above this green curve, we don't have any codes. And below this purple curve, we do have codes, and we don't know anything about the middle. Okay, so let me go into more details into this LP bound, because that's basically we're trying to generalize the approach of the LP bound here. So here, the LP bound is based off what is called the Del Sarti linear program, which is just this linear program here. So at this point, it's not that important how this program looks, but it's important that the reason why this gives an upper bound is because if I look at a code of distance at least d, I can compute what's called sometimes the distance profile of this code, which is just you count the number of pairs of code words of distance at least exactly equal to I, and then you plug this into this linear program, and you can see that's a feasible solution with value that's just size of the code, which just means that the optimal value of this guy is just an upper bound, right? Because it's just an upper bound for any possible code of distance d. Now, what's important to note is that this kind of convex optimization bound is studying 2-point interactions, and it's very natural to ask yourself is, well, if I were able to look into interaction between more points, except than just looking like at distance of 2 points, would I have enough information to perhaps give a better bound? And people have done this in the literature. So Shriver gave a 3-point interaction semi-definite program that gives, at least numerically, slightly better bounds. Later, he also improved this to a 4-point interaction SDP. And more generally, Lohan observed that you can do L-point interaction semi-definite hierarchy by noticing that actually there's a very natural independence number of a graph problem associated to this. And for that guy, you have what's called the Lasserre hierarchy. Now, granted, the underlying graph is exponential size. So if you just use the Lasserre hierarchy naively, you're going to have an exponential size program, which is pretty bad. But if you factor the symmetry of those guys, because there's a lot of symmetries inherited from the Hamming cube, you actually get something that, at least at constant levels, is polynomial size. Now, the advantage of the Lasserre hierarchy is that if you were able to actually run this thing in arbitrarily large levels, you know that this is eventually complete. Namely, if you were able to run at level 2 to the n, it would actually find the precise value of the best possible code. But the disadvantage is that, well, first, it's not a linear program, it's a semi-definite program, and second, it's very, very hard to actually analyze. So our work is to actually address this problem. And what we do is that we are going to provide a complete hierarchy of linear programs And it's not just a hierarchy of linear programs, but it's very structured. It's going to look very much like the Del-Sarti linear program, so that we have some hope of actually analyzing. Now, as you might expect from the title of the talk, it's really only going to work well for linear codes. For nonlinear codes, the hierarchy exists, but it's not going to be very good. Now, what's the idea behind of this? Well, recall that the Del-Sarti LP was studying these distance profiles, which were like 2-point interactions, and it was based on these Mac-Williams inequalities that are essentially some linear combinations of these numbers using what are called the Krochuk polynomials. Now, for us, we're going to study L-point interactions, so we have the notion of L configurations, which are the following. So instead of keeping track just of the Hamming weight, we're going to keep track of Hamming weight, all possible Hamming weights of all possible linear combinations of any L tuple of code words. So if I give you some tuple of code words, the L configuration is some function that maps from subsets of 1 through L to natural numbers that simply says, for example, if you evaluated that set 1 to 7, you take the first word plus the second word plus the seventh word, add them together, and you compute the Hamming weight. And the configuration keeps track of all these things. And analogously to the distance profile, we have the L configuration profile of the code, in which what we keep track of is you count the number of pairs of L tuples in your code such that the configuration of their difference is equal to a particular function G. And the idea is that we're going to prove some sort of higher order version of the Mac-Williams inequalities. There will be some sort of Krochuk polynomial such that this kind of linear combination is always non-negative. So what we're going to get is a hierarchy that looks very much like the Del-Sarti LP, because we're going to have one variable for each configuration. We're going to sum over all these variables. We have some normalization constraints, some zero constraint, the Mac-Williams inequalities, and some positivity constraints. And our intended solution is, of course, the configuration profile of a code that we saw before. And let me focus a little bit on this restriction here. This restriction is just saying, well, if my code has distance at least D, then when I do these kinds of counts, if my configuration G is such that there is a singleton coordinate strictly between 0 and D, well, the singleton coordinate is measuring the Hamming weight of the difference of exactly one code word with one code word. So it cannot be between 0 and D. So that forces the count to be 0. Now, on higher order, something different happens for linear codes. So if we have a linear code, actually this configuration profile is more easily computed by counting the number of tuples with a certain configuration. But this means that you can actually put up even more restrictions for linear codes, because even if I have a coordinate that's indexed by a larger set and it's between 0 and D, then I also know that it cannot happen because this set is counting the Hamming weight of a combination of linear of words, and my code is linear, so that's also a code word, and it cannot be between 0 and D. So you can actually put more restrictions, and this completely changes how the hierarchy behaves. Let me also point out that there's a small technicality with this hierarchy, which is the value corresponding to the solution is actually size of the code to the L, so you actually have to extract L effort, but this is just a technical detail. Now, let me just tell you what are these higher order Krochuks. So this is the usual Krochuk and the usual Mac-Williams inequalities, and as I said, we have a higher order version of this. And it's a more complicated formula, and I don't really want you to understand what this means, but I just want you to look and see the similarity of these two expressions. Like this is just an alternating sum of products of binomials. This is going to be some alternating sum of products of multinomials. And what I want you to get from this is that there is an efficient way of computing this. This can be computed in polynomial time, assuming that L is constant. And if you know a little bit about association scheme theory, it turns out that these higher order Krochuks are the Q functions of some specific association scheme. So they have similar properties to the usual Krochuks, like orthogonality, reflection, and recursion relations. Let me just finish by actually stating our theorems. So the first one is that this hierarchy is actually complete in the following sense. So as I said, it does give an upper bound for any code, but by level about n squared, you can prove that the upper bound is not really that far from the true value of the best possible code. This is when you use those extra restrictions that correspond to linear codes. Now, if you don't use those extra restrictions and you're studying nonlinear codes, it turns out that this hierarchy is complete garbage. It has all the values being the same, so it completely collapses. But so you should really use for linear codes. And let me finish by saying that even though it's not in the paper that was submitted here, now we have an even more complicated proof that shows that the hierarchy is actually complete not by level n squared, but by level n. And it's not even approximately complete, it's precisely complete. It finds the correct value of the best possible code. And that's all that I had to say. Thank you.
Thank you. Thank you for being in time. Any question? Suaz is hand raised. I don't know if it's by mistake or.
So do you know there are any concrete situations where this actually gives you something a better bound?
Yeah, we did run numerically for some very small instances of n and d, and it seems that it mildly beats the Shriver bound, at least numerically, but it's not very practical to run this hierarchy on very high levels. We run on level L equals 2. Higher levels, it seems like the complexity gets very bad very fast, even though it's still polynomial. We really want to propose this hierarchy to get actually an analysis of it rather than actually run it.
Another quick question. So you mentioned this distance profile, but you could look at the orbits of the actions on L tuples, and it won't be the same.
It won't be the same. So actually, Lohan's result on the Lasserre hierarchy, she's just looking at those orbits on the Lasserre hierarchy, and the problem is that once you factor the symmetries, you don't get a diagonalizable algebra, so you stay with the semi-definite program. This another way of seeing our result is to say, well, what if you drop some constraints on the Lasserre hierarchy so that you have more symmetries that when you factor, you actually get a diagonalizable algebra. So this is one way of seeing our work. And you want to retain completeness, and you do retain completeness.
Okay, thank you. Okay, so I think we are approaching our last talk. Jesco, are you
yes,
there?
hello.
There. Yeah.
Sadly, my webcam just broke, so the sound has to suffice.
So we will imagine you are there. Okay, so, but can you share your slideshow?
Yes.
Okay.
Can you see it?
The slideshow we can see.
Yeah, okay.
Okay, we can also hear you.
Okay.
Okay.
Oh, sorry.
Maybe I'll introduce you first.
Yeah.
Okay, great. Okay, so our last talk will be by Jesco Dudmovic. I probably don't pronounce it correctly. From CISPA Helmholtz Center. And this will be more about the applications of codes to cryptography. Thank you.
Yes, thank you very much. I'll be talking about algebraic restriction codes, which is something we defined in this paper. Those are my co-authors. So imagine you have a device and you want to input two vectors x0 and x1, and it publishes a scalar affine function of those two vectors, a times x0 plus x1. That's what it's supposed to do. However, it can misbehave, and instead of multiplying by a scalar, multiply by an arbitrary matrix A. So this will become a multivariate affine function instead of a scalar one. And this is what we want to prevent this while still allowing the above behavior. So what we do is we randomize x0 and x1 using some encoding function and some randomness R, and turn those into x0 hat and x1 hat, and give those two vectors to the device. Then the device can multiply, use the affine function to evaluate and get x0 hat plus x1 hat. And now we can also publish R, and then the public can reproduce a times x0 plus x1 as they were supposed to learn. However, if the device misbehaves and uses a matrix which is not just a scalar function, scalar affine function, then the public cannot reproduce any value dependent on x0 and x1, even with knowledge of R. So this is what the algebraic restriction code does. More generally, we have two sets, F and G. F is a subset of G, and we want to allow the functions in F. We want to allow functions in F, and disallow the functions that are in G but not in F. So the syntax of our algebraic restriction code is you take some input x and some randomness r, produce a encoded input x hat, and then you can evaluate a function from f or g on it and get an encoded output. Now this encoded output can be decoded using the same randomness, and you get y. And if the algebraic restriction code is correct, then this y that you get in the end is the same as if you evaluated this f function on the original input. However, if you use some function outside of f, then y should be uniformly random and not contain any information about x. This is the definition. I am not going to go into the constructions. We have two constructions of algebraic restriction codes. One which allows for scalar affine functions, where f are the scalar affine functions and g are the multivariate affine functions. And we have one where f are multivariate linear functions and g are all compressing functions. And this is our, I think, the technical crown jewel of the paper. And in a way, you need this compressing property. Otherwise, you can always reconstruct x0 or you can always reconstruct the input from the output. Yeah. Okay. We apply this in cryptography in a oblivious transfer protocol. A quick recap of what's an oblivious transfer protocol. It's a protocol where we have two parties, a sender and a receiver. The receiver contributes a choice bit B, and the sender contributes two strings, M0 and M1. And in the end, the receiver learns MB. However, she does not learn the other M, so M1 minus B, and the sender also learns nothing about B. This is a very important protocol in secure multi-party computation, as it is sufficient to do arbitrary secure multi-party computation. Using algebraic restriction codes, we get a oblivious transfer protocol under the DDH assumption, which has very nice properties. Namely, it is rate 1, which means this oblivious transfer 2 message is as good as it gets. It is statistically sender private. Only 2 messages are exchanged, and we don't need any setup assumptions, so no common reference string or random oracle model. To explain this protocol, I'll first go into what's linearly homomorphic encryption, which is something that we use. And a linearly homomorphic encryption is a kind of public key encryption scheme with special properties. In a public key encryption scheme, you have two keys, a public key PK and a secret key SK. And you can use the public key to encrypt so in our scheme, you can use the public key to encrypt a message which is a n by n matrix over the integers modulo p, and then you get a ciphertext C. And now if you use the secret key to decrypt it, you should get back the matrix. Now the specialty of linearly homomorphic encryption is that you can modify this ciphertext using two vectors A and B to get a new ciphertext C prime. And if you decrypt this ciphertext, you get M, the original message, times A plus B. Now, using this, we want to construct a linear oblivious transfer protocol. And this seems pretty easy. You just take the choice bit B, multiply a identity matrix to it, and encrypt it, and send the ciphertext and the public key to the sender. The sender can then evaluate the function, a affine function of M1 minus M0 and M0 on the ciphertext, and get a new ciphertext C prime and send this to the receiver. And the receiver can simply decrypt it and will get this value, which is exactly MB. However, in this scheme that in this linearly homomorphic encryption scheme that we use for the
Let's go. We need to finish like in 1 or 2 minutes.
Okay. Yeah, I'll be done soon. The receiver can misbehave and choose a matrix which is not just a scaled identity matrix, and this is exactly what we do use the algebraic restriction codes for. So instead of just inputting the M0 and M1, we encode them, get M0 hat and M1 hat, and now the sender, the receiver still behaves the exact same way. She encrypts the identity matrix and sends it. And now the sender will use those encoded values and send them back. And the receiver will learn this function and gets MB hat. She can then decode MB hat and get MB. However, if she misbehaves and uses a bad matrix, she will not get any result dependent on M0 and M1 because of the security properties of the algebraic restriction codes. That's it. For further details about the algebraic restriction codes and the cryptography around this construction, please check out our paper and I'll take questions.
Okay, thank you. And thank you for being on time. We're a bit over time. Maybe if there's just one quick question or something. Okay, since we are anyway over time, maybe we should stop now. So thank you, everyone. Thank you all the speakers of this session. Okay.
Thanks, Noga.
Thank you. Bye-bye.
Thanks. Bye-bye.